بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد عليه أفضل الصلاة وأتم التسليم. Today we're going to present about computerized tomography in a brief. Imaging is an important part of diagnosis because it allows for non-invasive or minimally invasive pictures of body organs and tissue without the intervention of a surgery in some cases. This improves the healthcare profession as it allows for accurate results and accurate diagnosis. One of the technologies used for body imaging or imaging in diagnosis is CT scan or computerized tomography. We're gonna go over the device history, some literature review, theory of operation in clinical settings, how to maintain and install such devices, and some ethical issues and cases related to these devices. What is CT imaging or CAT imaging? CT is an abbreviation for computerized tomography, or in some parts of the world, computerized axial tomography, which is CAT scan or CAT imaging. It is an imaging technique used to generate 2D or 3D pictures or slices of the body, tissue or organ, generally used for diagnosis purposes. How does CT scanning operates? CT scanning operates on the principles of taking multiple pictures in different angles of the body or the tissue and then running those pictures through a computer with an algorithm to construct a 2D image of the tissue or part as shown in the picture. Thus comes the name computerized tomography, in which tomography stands for multiple slices or sections in Greek. The development of CT imaging began in the 1960s and 1970s with the first commercial available CT scanner made by Godfrey Hounsfield in 1972, working with EMI laboratories. Godfrey also co-invented this technology with physicist Dr. Alan Cormack. It's also important to note that Godfrey's work was built on two important mathematical models: Radon transform in 1917 by Johann Radon and Stefan Kashmer's algebraic reconstruction technique in 1937. Moving to the literature review, we'll go through the different generation of CT scanners, beginning with the first generation as shown in the picture on the left, with one X-ray source and the pencil beam design with one X-ray detector that move in a rotate transverse motion, similar to the one in the middle picture, which is the second generation with multiple X-ray sources with pencil beam design with a multiple array or a single array of X-ray detectors. Then we move to the third generation, which is similar to the fourth generation in its design, with a single X-ray source with a fan beam design moving in a rotation motion, a 360-degree motion, with combined with its own row of detectors, or compared to the fourth generation, which has the same source, X-ray source and beam design, but instead has a stationary ring of X-ray detectors. Then we move to new improvements in technologies in state-of-the-art CT scanners, which include a cone beam design for the X-ray source, scintillator detectors, which include multi-layer detectors and multi-row detectors, improvement in cooling, which allow the device to run for a longer amount of time and produce less amount of noise, some power management, which allows the device to run more efficiently, dual energy design, which allows the device to take two different X-ray images at different contrast rates in a single run, noise reduction, and the spiral helical CT, which reduces the runtime for a full body scan or a scan in general of the CT scanner. Here we have an example of a state-of-the-art scanner, which is the Toshiba Aquilion 1, which has a 0.5 millimeter by 320 detector layers 640 slices for every rotation, a full rotation time of 0.35 seconds, and a beam width of 160 millimeters, and more other specifications. The theory of operation for CT scanners can be split into two parts, the data acquisition and the image reconstruction. In data acquisition, we'll focus on the X-ray tube and the detectors. The X-ray tube is basically a glass tube, a vacuum sealed glass tube that is the source of the X-ray beam itself, with two separate circuits, one for the electron beam that produces the electron beam that then hits the tungsten anode, which produces the X-ray beam itself. The tungsten anode is placed on a rotating plate to be able to use two settings for the X-ray beam, either a larger area beam or a smaller area beam. That beam is then filtered through different filters to control the size and the amount of dosage per patient, and so on. The detectors are two different types of detectors. The gas detectors, or the inert gas detectors, which are no longer in use, which uses neon gas that is ionized by the X-rays, and that ionization produces an electrical signal or electrical impulse that is then passed through the insulator at the bottom. The newer detectors, which is the scintillator detectors, uses scintillator substance to convert the X-ray into photons, or basically visible light, that is then detected by photodiodes, and then they are passed into as electrical signals into the computer to be processed. Before going into the computer, the signal passes through the different signal conditioning blocks in order to be able to be processed by the computer. Inside the computer itself, it goes through the image reconstruction process, where different methods are used, such as the Fourier transform, simple and filtered back projection, a series of mathematical expansions, such as the algebraic reconstruction techniques, in order to construct the 2D image of the slices. Filtered back projection is, as shown in the picture below, is basically taking the different pictures or slices at each angle and then smearing them on top of a picture at the angles they were taking, which results as shown in the picture below. Moving to operation in clinical settings for CT scanner, first we begin with setting up for the procedure, where the technicians does calibration on the CT scanner itself, depending on different measurements for each patient, depending on the procedure itself, if it's a head scan, chest scan, and so on. The procedure itself takes about 15 seconds to a few minutes, depending on the procedure, if it's a head scan or a full body scan. Some applications for CT scanners include different organ perfusions, angiography, or image-guided surgery, 3D imaging, and so on. And as we can see from the picture here, here it's an application for angiography, where it's spotting possible clot in the brain, and 3D imaging of the heart. Maintenance and installation requirements are dependent on the country the CT scanner is being installed on or being operated in. For Saudi Arabia, we have the Saudi Food and Drug Authority and Ministry of Health. But generally, the installation requirements includes a room with sufficient radiation protection, such as full shielding of radiation, lead shielding, deadline doors, and the floor must be able to accommodate the weight of the machine plus the patient and any other operating equipment. For general maintenance, different maintenance procedures are specified by the manufacturer and are usually done by a third party or a technician from the manufacturer itself. But usually they include yearly tear downs, where the devices are teared down and inspected thoroughly, or periodic monthly or bi-monthly calibrations, where it might include software updates, cleaning of the equipment, and so on. Lastly, we look at ethical issues and cases regarding CT scanners, such as patient safety, radiation dosage, necessity, cost, and benefit versus harm, where sometimes certain healthcare professionals might prescribe CT scans where it's not necessary for reasons such as to cover up the costs, and sometimes they neglect patient safety with radiation dosages. And sometimes doctors or healthcare personnel need to weigh the benefit of the actual scan versus the harm the scan does on a patient. And as we can see from the picture, a typical CT scan is much higher in radiation compared to a normal X-ray scan, where it takes about 511 days of natural radiation, which equates to a normal lower back CT scan. In conclusion, we learned about CT scanner and its importance in imaging diagnosis. We learn about the device history, some of the state-of-the-art technologies involved in it. How does it operate? What are its basic principles? What is it used for in its different applications? Some installation and maintenance procedures for it, and the different ethical issues regarding CT scanners. At the end, I'd like to thank you for your attention, and please don't hesitate to ask me for any question you have through WhatsApp.